So good morning, class. Here we are again on a snow day. Thank goodness that I can do these videos because that helps me avoid getting out and killing myself in the snow, and I hope it helps some of you too. Let's talk about the first of our two algorithms today, and that is how to make a complement finite state machine. It's often the case that you'll want to do something like strings that do not have a multiple of 4 A's in them, or strings that do not contain A, B, B, A, something with a not in it at any rate. And this algorithm makes that really easy. So think about this first paragraph here that you can see on the screen right now. It says that if a machine is deterministic, then any string that you run through that machine has only one pathway that it takes through the machine, one set of state changes. If it's non-deterministic, of course, you might end up with more than one way to run a string through the machine, but we're talking deterministic here. And in that case, a string will always end you up in the exact same state at the end of that particular string. And if that state is an accept state, then the string is accepted, otherwise it's going to be rejected. Well, what would happen if you took all of the non-accept states and turned them into accept states, and all of the accept states and turned them into non-accept states? Well, then that machine would accept every string that it used to reject, and it would reject every string that it used to accept. Isn't that right? Take a look at these machines right here. This is the odd even machine. This is a machine that you should recognize by now. It's that parity of two letters machine. So this is where you are if you had an even number of A's and an even number of B's. This is odd, even, odd, odd, and even, odd. And it's kind of hard to tell here, but we've made this state be an accept state. So this machine is accepting strings that have an odd number of A's and an even number of B's. If we flip the states to the opposite type throughout the whole machine so that this one becomes a non-accept and these all become accept states, then this machine accepts every string that this machine rejects, and it rejects every string that this machine used to accept or accepts. So these two machines are complementary. Now what that means is that no matter which string of A's and B's you pick, one of these machines will accept it, and only one. So every single string is going to be accepted either by this machine or by this machine, never both, and always one. That's the case when two machines are complementary. Now, there are some caveats here to our algorithm. Take a look at this machine. This is a machine for strings that start with A. Look at this now. Is this the complement of that machine? The answer is not entirely obvious because it looks like it ought to be. However, there's something going on here. I'd like you to think for just a minute about what happens if you run the string B or BB through these machines. If they are truly complementary, then exactly one of those machines will accept that string. Does this machine accept the string B? No. This machine has an implied trap state. So that if I draw, let me draw on this machine. If I make the trap state explicit rather than implicit, that letter B takes me to this trap state where I stay for the duration of the string. In order for this machine to have been a complement of this one, what would have happened to that trap state? It would have become an accept state. And so this would be the complementary machine to that first one, where the trap state is now an accept state along with that initial state. So you must make sure before you do this algorithm that your machine is deterministic and that any trap state has been made explicit and not left implicit, or else that you just remember to add the trap state and make it an accept state. Let's take a look at these machines now. I've been saying that it's necessary for the machine to be deterministic before you try to take its complement. And I want to show you a case now that just reinforces that idea. Take a look at these two machines. This one and its look-alike, but with its states flipped. Run the string A through this machine. Does it get accepted? Well, it does if you go that way, but it doesn't if you go that way. So there's more than one pathway for that string. How about the string BA? Well, BA gets accepted. What about BA? It doesn't get accepted. Over here, BA doesn't get accepted. BA does get accepted. If both these machines accept the string BA, or both these machines accept the string A, then they cannot be complements of each other. If they truly were complements, then a string would get accepted by exactly one of the machines. Any string made out of A's and B's would get accepted by exactly one. If a machine is non-deterministic, then you can't use that algorithm where you just flip the state types and expect to produce a complementary machine. Now, let me just show you one more time why this algorithm for taking complements is so useful. Suppose I want you to make a machine for strings that do not contain the substring BAA. Well, we know how to make a machine easily for strings that do contain BAA, so we would do that. And then we would run our complement machine. Now, if we were doing the does contain BAA substring machine, this would be an accept state. So we'll just remember that for a second so I don't have to erase. But if, let me just finish the machine and add my missing edges in here. B goes there, BAB, BAB needs to go here. Alright, so the positive does contain BAA machine would have this as an accept state. I do not need a trap anywhere. Every state has an A and a B. It is a deterministic machine, so my complement algorithm would just tell me to turn these states right here into 3 accept states, and that is the machine for strings that do not contain BAA. Easy. Alright, now, the rest of this handout on complementary machines has you do a little summarizing of what you know, and now is a really good time for you to do that. And then it asks you to come up with a way that you could find a complementary regular expression. Suppose you have a regular expression for strings that contain even A's and even B's. That regular expression is really long. Do you remember what it looks like? Not a bad time to just get this in your head again. Even A's and even B's. Kind of a long regular expression. Looks like this. Whole thing starred. What if you want a regular expression for strings that do not contain an even number of A's and even number of B's? In other words, the complement of that. We do not have a direct algorithm that just takes a regular expression and munges it around in some way to produce a complementary regular expression. Don't have that. But we do know something about how to take a regular expression and turn it into a machine. And we know something about how to take a machine and find its complement. And we know something about how to take a machine and extract from it a regular expression. So put all those ideas together and write down a little algorithm for finding a complementary regular expression. It won't be pretty, it would take a while to run, but it is possible to do, and if you really had to, you could do it. Now you finish that worksheet while I edit this one, and then I will make the other one, and you can watch the other one.